Okay, welcome to Let's Get to the Marks, looking at a question on the isomerism and dehydration of alcohols. So here we're looking at question two. This is from the 2023 AQA Chemistry A-Level Paper 3. Pentan 2O has the molecular formula C5H12O. Draw the display formula of an unbranched position isomer of pentan 2O that can be dehydrated to form a single alkene. So we need an unbranched, so we need to follow the instructions here. Let's zing out that unbranched chain. Make sure you pause the video, have a go on a scrap bit of paper, or in your head, just try and work it out before unpausing and watching me explain it. So that accounts for the unbranched position isomer. Now, they were saying that the OH was on the second carbon. We could move it to the third or the first carbon. They're the only two positions. You can have pentan 2O, pentanol, or pentan 1O, and pentan 3O. They're the only unbranched ones you have. So you've only got two choices, pentan 1O, pentan 3O. In this case, it's going to be pentan 1O, because if we do pentan 1O, we can dehydrate this to form one type of alkene only. There's only one alkene that can be formed from this, and that is pentene, pent-1-ene. So you can't make pent-2-ene, pent-3-ene from this molecule. So this is the correct answer. Okay, let's move on. Now we've got question 2.2. Draw a skeletal formula. Cool. Right, question 2.2. Draw the skeletal formula of a chain isomer. So now we're told we have to disrupt the chain. So we can't keep it as pentan. We're changing the chain. So it's going to be like methyl butanol or something like that. So draw the skeletal formula of a chain isomer of pentan 2O that can be dehydrated to form a mixture of different alkenes. So it can form more than one alkene. And what we're looking at here, peeps, we're going to want something along the lines. Now it says skeletal, but I'm doing the display just to help with the explanation. So if I just draw like, now we know we need to change the position. So for example, if I put a methyl group here, this is now butanol, right? This is 2-methyl or 3-methyl butan 2ol, whatever. So that is basically, we are able to form two different alkenes here. As long as the carbon atom, you see this carbon atom here and this carbon atom here, as long as they possess a hydrogen that is then going to, because what happens when you dehydrate an alcohol is the carbon adjacent to the carbon with the hydroxide group donates its pair of electrons from a hydrogen to the double bond. So here we'd be able to form like 3-methyl butene, sorry, 3-methyl butene, or we could form what would the other option be? 3-methyl butan 2-ene. So this one here can form two different alkenes. So that is our chain isomer. I've changed the size of the chain. That can do that. Of course, there's a hydrogen atom there. So we want to draw this out in a skeletal formula. So it's a couple of ways you could draw this in a skeletal formula. So oh, I could have done a methyl group there. Doesn't matter. Whatever, I'll put my methyl group there. So there you go. That's what they're looking for, a skeletal formula. I could swap the OH group and have the OH group there and the methyl group there. It doesn't really matter. Same molecule. So this can form two different alkenes. Okay, let's look at 2.3. Draw the structure of an unbranched, a lot of isomerism here, gets my head spinning. Draw the structure of an unbranched functional group isomer of pentan 2O. Right. So what you need to know for this one is we need to know that you need to keep checking back to the molecular formula with isomers just to make sure that it's C5H12O. So what you might try, you might say, okay, I need to do an unbranched. What does that tell you? That tells you that we have 5 carbons, that we're going on a 5-carbon trip. unbranched functional group. It's a straight chain. We can't have any methyl or ethyl groups coming off. So that's what that tells me. And then you might start playing around and going, what about pentan? Three own, but once you start counting up the hydrogens, you go five, six, seven, eight, nine, 10. You're like, oh, I'm too short. And then you might say to yourself, all right, what about if I do an aldehyde? That's going to get me um, more hydrogen atoms potentially. So if we zing over here and we do like pentanal like that. What do we reckon there? So we're going to go one, two, three, four, five, six, seven, eight, nine, 10. No, we're short again. And after a while of playing around with this, hopefully you might be able to come up with, you don't necessarily have to know how to name it, as long as you can come up with a molecule that's unbranched with that formula. Don't worry about naming the molecule. Okay, and what we can do here is we can just put an oxygen atom in the middle, because of course oxygen can have two bonds, so this can go in the middle of the carbon chain, and we can have that ethyl group and a propyl group either side of that oxygen. So yeah, super duper duper. Now you could draw that as a skeletal formula, or you could draw that as a structural formula. If you're going to do like I have as a displayed formula, you need to make sure you put the H's in. I'm just being lazy and not putting the hydrogens around the outside, but there you go. That's going to get you a mark and get you that point. Quite a difficult question, but I recommend just having that molecular formula up there is what allowed me to work it out. Okay, so now we go 2.4. Another isomer of pentan 2 is an alcohol that is not dehydrated when heated with concentrated sulfuric acid. So this is one that will not undergo that mechanism of dehydration. Draw the structure of this isomer. So we're looking at a molecule that cannot form an alkene, even though it has a hydroxide group. So pause the video, have a go. All right, I'll go through what the answer is here. And again, I'm drawing the old displayed formula, but you know, it doesn't have to be a displayed formula. A lot of people prefer not to. So what we're going for here, we might go for like 2,2. This is the second carbon in the chain down here. I'm going to go 2,2 dimether. So I'm having two methyl groups coming off the second carbon. And then we need one more carbon atom, don't we? Because 5 carbons in pentanol. And there we go. So you might say to yourself, hold on a minute, how come that can't form an alkene? But remember what happens with alkenes. Remember, what we need is the carbon atom adjacent to the carbon the hydroxide group's on has to have a hydrogen. So ideally, if you want to form an alkene, then, oh God, this is pretty terrible going. Right. This carbon atom is the important one to know whether your alcohol can form an alkene, not the carbon atom, the hydroxide. So not this one that the hydroxide's coming off, but this one, because this would normally have an H that will slap down and donate that pair of electrons to the bond there to form the double bond. But what we find with this dimether is that there are no hydrogens on that adjacent carbon atom that's attached to the carbon with the hydroxide. And so that means that there isn't a hydrogen atom to snap off on this carbon atom and form a double bond there. So yes, this cannot be dehydrated to form an alkene, even though at first we might look at these two H's here and say, hey, aren't they going to do it? No, they're not the ones that do that. It's the H on the carbon atom adjacent to the carbon with the hydroxide group. So this carbon atom here. Okay, let's move on to the next part. Oh my gosh, what am I doing there? All over the chip shop. Right. Oh my days. Scroll down, Tom. Okay, so what we got going on here? We got question 2.5. An incomplete mechanism for the dehydration of a compound is shown. Complete the mechanism for this reaction by drawing two curly arrows on the intermediate. Name the mechanism for this reaction. So we can see here there's a lone pair of electrons going to the hydrogen there. All we got to do is come over here, and you might be like, how the hell am I going to work this out? Look at the finished product. What's happened? Have a look. There's a single bond here, have a look at the finished product. Double bond. Where's that double bond come from? Hello, there was a hydrogen atom there, wasn't there? So what do you think has gone on there? Well, just like we have been doing in the previous talking about dehydration, we obviously have a curly arrow coming from this hydrogen. This hydrogen is going to leave the situation and it's going to donate its pair of electrons to form that double bond. So you should have been able to work that out from this, but also what's going on here? We've got this oxygen with two hydrogens, an oxonium ion. So we've got this situation going on. We've got this plus charge here, and we got this bond here. So we need to really resolve this issue. And the way we're going to do that is the bond here is going to put its electrons here to get rid of that plus, and we're going to have the elimination of water. So we got this situation going on. Those are our two curly arrows, and we can tell that's what's happened because look over here. Where's the OH2 gone? It's disappeared. So we've had a water molecule vacate the situation, and we've had a hydrogen atom or ion vacate because it's no longer a hydrogen atom. It's donated its electrons to form the double bond. So that is going to pick you up a couple of marks for the two curly arrows. And then the name of the mechanism, this is some sort of elimination reaction. They'll probably ignore whatever else you put in front of the word elimination. You'll probably get the mark. So just it's elimination because we're losing that water molecule. Superbulous. Obviously, we can't really say we're losing a water molecule and a hydrogen ion because look, we started by the addition of a hydrogen ion. All right, so can't really say we're losing water and a hydrogen. Overall, there's just a loss of a water molecule. Anywho, that is 3 marks. Let's move on. Let's go down to 2.6 in the final part of this question on isomers and the dehydration of alcohols. So an isomer of the final product can form in the reaction in question 2.5. Draw the structure of the isomer. Oops, I need to have a look at that final product. What does it look like? So we can have an isomer of this bad boy. So, okay. So we could have, we've got this. So we could have the double bond. If you look here, the double bond could have formed here. And oh God, this is looking really messy. But the double bond could form there or there. It actually formed over here, but it could have formed here as well. Well, this CH3, one of its hydrogens could have broken off to leave CH2. So all we need to do is redraw this molecule here, but with a CH2 there and change the position of the double bond to here. So let's give that a little go. And obviously we want to leave that H because that H hasn't vacated in this situation. So let's draw that. Oh gosh, not doing a good job here, right, peeps? We're going to draw the same thing out. So C6H5. We're going to go to double bond N O. Not looking good. C. I'm going to draw this a bit to the side. CH2. So what's happened here is one of the hydrogens from the CH3 there has donated its electron here to form the double bond here, which means that this would still be like that and would still have a hydrogen there. So that hydrogen hasn't broken off. The hydrogen from the CH3 has been sacrificed to form the double bond. And that should be the molecule we are actually looking for. So lovely jubbly. Bit squished up there because I tried to fit it in with that question so I could talk about it at the same time. Hopefully you understand that. If there's anything you didn't understand about that question, just pop a little something in the comments and maybe I can get back to you as soon as possible with a reply. All right, guys, let's get to the marks.
You're still here? It's over.